Hello everybody, welcome back to another video of me trying to learn the Zig programming language with the goal of understanding systems programming in better detail. So for those of you who don't know, we've been following this fun little course called Ziglings created by Chris Bosch. And the idea of Ziglings is you solve fun little exercises, which is fixing small programs, getting it to build and run locally. And towards the end of following the exercises, we would have a foundational understanding of what Zig is all about and the idiomatic way to express ideas and thoughts in Zig. And in today's exercise, we're going to be doing pointers. I am very excited for this. I've been looking forward to it for a while. Pointers is a really fun and interesting topic. I know it can get quite cumbersome and quite dangerous if we don't truly understand it and get the science down, but it is nevertheless a very fun topic. I'm excited that this is probably one of the most one of the constructs that I'm really excited to learn. So yeah, we'll do all the pointers, exercises, and the quiz too in this video. So very excited for that. Let's not waste any time. Let's dive right in. Cool. Let me read through this. Check this out. We have the variable foo and we have the variable bar. When bar is being assigned to foo. Now it clearly says foo is 5, but bar is a pointer to foo. How do we know this? Very clearly, we see that this special operator here, which is the ampersand operator. Essentially what this is doing is it's going to say assign bar the memory location or the reference of this variable foo, which is why we see an asterisk before the type definition. And this is important. It's saying bar is an unsigned integer of 8 bits, a pointer of unsigned that points to an unsigned integer of 8 bits. So cool, let's go and read through it. What is a pointer? It's a reference to the value. In this example, bar is a reference to the memory space that currently contains the value 5. Yep, we understood that. A cheat sheet given the above declarations. U8 is the type of an unsigned integer of 8 bits. Foo is the value 5. Pointer to U8 is the type of a pointer to a U8 value. Ampersand foo is a reference to foo. Bar is a pointer to the value at foo. And bar dot pointer is the value 5. Ah, interesting. Usually in languages that I have seen, which is I believe C, maybe C++, generally we do something like this to access the memory location, and we just write bar. That would be the memory location, whereas putting the asterisk would give us the value held at the memory location. But in Zig we have the dot access operator where we use bar and we say this is very expressive, I like this, and we get the value using the still predominantly popular asterisk operator for pointers. I still like that they kept that. Cool. We'll see why pointers are useful in a moment. For now, see if you can make this example work. Cool. I'm not going to compile this because I know it's just going to throw a syntax error. And we know what we're trying to do here. We're saying num1 is unsigned integer of 8 bits. Num1 pointer is a pointer to the unsigned integer of 8 bits variable, which is num1. Cool, and we have another number, and now it's the value which is unsigned integer of 8 bits. Now how do we do that? Please make num2 equal to 5 using the num1 pointer. We just saw right here how to do that. Now let's try it. We'll say num1 dot asterisk, right? I misspelled num1 pointer. Cool. This will give us the value held by the memory location that num1 points to. And that should give us the value. Let's run that and see. 039 pointers. Yes, that is perfect. So we understood that num1 is a value type. So there is an address space in memory that holds that value. Cool. Yeah, so essentially we have two address spaces. We have the num1 variable here, and we have the num1 pointer here, and the num1 pointer holds the address of num1, and we can access the value held in num1 by using the amp the asterisk operator, which will essentially tell the compiler to say go to the value held, go to the num1 pointer, see the memory address, then go to the memory location and get the value. Cool. I think that makes a lot of sense. Again, very interesting topic. Let's move on and we'll learn slowly. Second exercise. Now, it's important to note that variable pointers and constant pointers are different types. Given var foo is equal to unsigned integer of 8 bits, constant bar is unsigned integer of 8 bits, then ampersand foo is of the type pointer to u8, whereas ampersand bar is a type of pointer to constant u8. I did not know this. This is a new concept for me. I don't know if C has this. I cannot recollect. I have not personally written something like this where a constant pointer was uniquely different, but maybe it is. Let's see. You can always make a constant pointer to a mutable variable, but you cannot make a variable pointer to an immutable variable. Okay, I would like to understand the significance of this. I understand the statement, but I don't understand its implications. So let's see. Yeah, this sounds like a logic puzzle. Yes, it is, because it just means that once data is declared immutable, you can't coerce it to a mutable type. Okay. Think of immutable data as being volatile or even dangerous. Zig always lets you be more safe and never less safe. That I really like, really appreciate, but I want to read the paragraph again and see if I can paraphrase it myself. Again, I get what they're trying to say, but I don't truly understand the implications. So it says you can always make a constant pointer to a mutable value. So there's a value that can keep changing, but we can have a constant pointer that always points to it. Okay? But you cannot make a variable pointer to an immutable value. I still don't get it. I would assume it should be the other way around. Why is a constant pointer allowed to point to a mutable variable, but a variable pointer cannot connect to an immutable variable? I understand. The next line has the key. So when something is marked immutable, it cannot be coerced into a mutable type. I get it. I get what they're trying to say. They're trying to say that, see, when something is marked as a constant pointer, pointing it to a variable isn't really bad, because the pointer, the value held by the pointer, the memory address will always be constant. So it is fine. But say we had a variable pointer pointing to a constant value. From the perspective of the variable, it is nothing much has changed, but from the perspective of the constant placeholder, a location in memory where we've said value is constant, it'll never change. That is now indirectly we're attempting to change it by assigning it to a variable pointer, and that's not allowed. Makes perfect sense. I believe I get it. It's a little bit to wrap your head around, but then it wouldn't be a different paradigm of learning systems programming and these low level languages without changing our preconceived notions of how a programming language is supposed to be. Just because it makes sense to my brain doesn't mean it's logically sound for all scenarios. Um, but I do understand the intent, but I feel like we'll have to come back to this particular paragraph. I just need to save it off somewhere and just reread it as I learn more about pointers, because there's a lot of meaningful concepts hidden here. Cool. Let's take a quick look at the program. So now we have imported the standard function. We have an integer integer constant, and we have an integer constant pointer. So b points to a, and we're printing the value of a and b. Both of them will be 12. So we're printing the value of a and the value held in the memory location pointed to by b. So it's not really a copy. Change in a would mean b also changes, but I'm sure it'll be shown later. Let's run this for now. 040. Oh, something is wrong. We need to fix it. Oh, I know what's wrong. And good thing we ran it without fixing it. It's saying, hey, you're assigning this particular value to just U8, but you can't do that because A is a constant value. So when we're getting the reference to it, it should be referred to as a type of constant pointer of unsigned integers. So, and the compiler is telling us that very clearly, and that's really great that it's explaining, it's being expressive and saying cast discards const quantifier. Cool. Let's try this again. Perfect. A and B now point to the same value, and it works. Again, technically, A points to a value, B points to A, which has its value. Cool, that makes sense. Let's see, let's look into the future. Ooh, okay. When you allocate memory, you store the returned address in a constant variable. The pointer itself never changes. It always refers to the same allocation, exactly what I was thinking in my mind too. A constant pointer only means that the address held by this particular placeholder in memory will always be the same. Now, the value held in the address can change, which is fine. Cool, but you can still read and write data that it points to. This is precisely why Zig prevents constant values, constant identifiers from being assigned to variable pointers. Kind of makes sense. Yeah, kind of makes sense, because we don't want somebody to access the memory location held by this variable pointer and then essentially find a loophole through Zig to change the value of the constant variable. Because if we have the address of a location in memory, modifying it wouldn't be too hard. So Zig's constructs prevent this from happening. So an example, const buff probably stands for buffer. Try allocate, so that's unsigned integer of 8 bits. We're going to allocate 1024. Is it bits? Bytes? What's that? Let me remove this. Okay, I think this is another library. We'll leave it commented. We'll come back to it. So this finds that the contents are mutable. Okay. We have a try syntax here as well. 1024 is a whole host. I wonder if this is bits too. Yeah, I think so. Passing this pointer to a function is cheap. It's just an address copied on the stack. A caller can work with the data without needing to know where it came from or how it was allocated. Understandable. Similar to how we have enums and structs, and it allows us to a lot of these data types. Again, if looking at it from the perspective of an object-oriented language, it makes perfect sense to makes it easier to make sense, because a lot of these sort of um, data types serve as an encapsulation. So we have a whole bunch of logically related data and ways of manipulating that data, and constructs like structs and enum, they're a way to package that into an easy, logically sound unit that can be passed around. And pointers are one such thing, because we saw here we are essentially creating um, a whole bunch of memory locations, and we're assigning it to this particular identifier. So it starts from there, and then we can keep addressing all the subsequent places in memory where up until its max size. Cool. I think this exercise makes sense. Let's jump on to the next one and see what we have in store. Cool. The tricky part is that the pointer's mutability, var and const, refers to the ability to change what the pointer points to, not the ability to change the value at that location. Okay, makes sense. Yes, yes, which perfectly makes sense. So const locked is unsigned integer, var unlocked is an unsigned integer. Now we have p1 that points to locked and p2 that points to unlocked. Now p1 has to be a constant pointer. We read this. And p2 can either be a constant pointer or a variable pointer. It doesn't matter. And we read that rule previously. And let's dive deeper into it. Now both p1 and p2 point to a constant value which cannot change. However, p2 can be changed to the point to something else and p1 cannot, which makes sense. A constant pointer just means that the address that it holds will never change. A variable pointer means that the address that the pointer holds can change. The caveat being the address of a constant value can only be held by a constant pointer. Here, P3 and P4 can both be used to change the value they point to, but P3 cannot point to anything else. Correct. Correct. What's interesting is that P5 and P6 act like P1 and P2, but point to the value unlocked. Let's see, P1 and P2, P5, P6 act like P1 and P2, but point to the value unlocked. Yes, constant pointers are pointing to a variable, which is allowed. Yes. I think I understand this, yes. Yes. Yes, I think I understand this more. Maybe when I was expressing when I was thinking out loud, maybe didn't think it out perfectly, but I do understand it. I'm gonna retract one of my statements. I'm pretty sure I said this incorrectly. So a variable pointer can still point to a constant value. Never mind. No, it cannot happen that way. Never mind. It's the other way around. My bad. My original statement was correct. A variable pointer can point to a variable, but a variable pointer cannot point to a constant value. Yes, a constant value can point to either a constant or a variable. Yes. I'd have to revisit this again. I grasp it. I'm excited about it. I can grasp it, but I need to come back and do it a couple of times and hone in that understanding. Why? So, one of the explanations that was given in the previous exercise, I did understand. There's a constant value. We do not want to assign it to a variable pointer. Um, but why? One of the reasons was, again, we don't want an immutable type to be encompassed by a non-immutable type. That makes it inherently less safe. How? I mean, from language semantics, we can prevent still updates, uh, modifications to the value held here. But I believe it's a case of Zig being very cautious in saying no. If it's a constant pointer, it makes no sense why you're assigning to a variable. If it's a constant value, it should make zero sense to assign it to a variable pointer. Why? Why are you doing that? Which kind of makes sense. Cool. Let's dig into the exercise. Please define pointer p so that it can point to either foo or bar and change the value it points to. So we need to be able to have this point to either of these things. So immediately we know that this needs to be a variable and its type needs to be a pointer. So it's asterisk and U8. And now we have a whole bunch of code that first assigns it to foo, increments it, assigns it to bar, then increments it. So final value will be 11. But we're still displaying foo and bar. Cool. Now, before I run this, because it's a pointer to a memory location, foo will now be 6 because we incremented it by 1, and bar will be 11. Because using a pointer to modify does not modify some copy of the original variable. It modifies the original variable itself. It's just an address reference. And this is why it helps to use pointers in certain instances, but it can also make it incredibly convoluted if you don't truly understand how they work. That kind of makes sense. Let's go to the next exercise. Now let's use pointers to do something we haven't been able to do before. Pass a value by reference to a function. Again, fizzbuzz, foobar, and a couple of other examples like hello world are quite synonymous with introduction to programming languages and computer science in general. One of the more popular examples are also pass by value or pass by reference. And in Zig, pass by reference happens through pointers. In languages, higher level languages like C#, they don't expose pointers. Maybe they do to a very, very, very specific extent. But languages like C# have like the out keyword or have like the ref keywords to pass by reference. But in Zig, obviously, if we have the ability to use pointers, we should use them. Cool. Provided they have a valuable use case. And we want to, I also believe it does save memory to an extent. Yes, it can. Now, pass by reference when you want to change the pointer to value. Otherwise, pass by value. Makes sense. Pretty straightforward. Now, cool. Looks like we're importing the standard library. We have a main function. We have a variable, and we have another variable, which is an array. Now let's pass the number reference to our function and print it. So to make 5, we're printing the reference, which is the address of num, and now make 5 can use the value held by the address and do its computation. And we're printing the value, final value, and then we're going to call make 5 on the next index. Here we're passing it by reference as well. and we're going to print it. And then we're going to loop through this entire array, and then we're going to see what it outputs. So let's complete the function. Right off the bat, we're passing in a reference of unsigned integer of 8 bits. So I'm going to say make 5. So it'll be x multiplied by 5, but with x multiplied by 5, x holds the memory location, the holds a memory address to another variable. So we'll do this, and that'll say, hey, the value held by the memory address in x, your value, I want it to multiply by 5. Let's run it. Cool. Okay. So we see that for each of the values here, for the first one we called make 5 of a number, and we'll say that's nothing but the number equal to 5 into 5, and we have that here. And then for the rest of them, for each of the numbers, not for each, for just the second number here, we made that third number. So because it's 0 based indexing, 0, 1, 2, we made that 5 because it's 1 into 5. Perfect. I think I understood what this portion of the pointers. So we can either pass values by arguments by values to functions, in which case a copy is made in memory. It does consume some extra extra memory space, but depending on what we're passing, it can potentially be smaller than pointers. But in pointers in general, there's no copying of data, just memory address moves, and the pointer can just look up the memory address and make any computation at once. So we are I would not use the word like saving space or the space complexity is better, because it would be inaccurate, because even a constant pointer still needs to be stored somewhere, and that will occupy some amount of memory to store the address to where it points to, but it can or cannot be more efficient depending on the use case. Cool. Let's look at another example. As with integers, you can pass a pointer to a structure when you wish to modify that struct. This use case makes a lot more sense because structures can encompass a lot of things, and this encapsulation passed by pointers makes significant sense when we're trying to modify the original value of the struct. Instead of reassignment, we can directly modify. Pointers are also useful when you need to store a reference to a struct. Yep. Cool, we have a structure here, and we have another structure here called where we're taking this type and we're assigning it to v1, and for pv we'll say, hey, this is a pointer, it points to the location of v1. Note that you don't need to determine the pv pointer to access the field struct. Dereference the pv pointer. Okay. pov.x will work directly, and we don't have. This is very similar to how Go does some of its things as well, I believe. Am I right about Go? Yes, I think so. Where we don't have to dereference it and then we can directly do it. Maybe I'm wrong about Go. Regardless, makes sense. It is a shorthand, or it is the right way, because this will not work, I believe. Cool. We can write the functions that take pointers to struct as arguments. Makes sense. Pointers to structs, it can be an argument. Again, it's a valid type. Functions can have most types. And call them like so. We're calling foo, and we're passing in the address of the memory location that needs to go through, which makes sense. Now, let's revisit our RPG example and make print characters function take a character by reference and prints it, and prints a linked mentor character if there is one. Okay, I see. Now Let's look at the standard library that's imported. We have an enum class, we have a struct here. Now you can use the default values. Okay, I need to use question mark here to allow for a null value, but I don't explain it until later. Very straightforward syntax. I've seen this syntax before. Nullability is an important concept. Because we're passing it to null instead of saying undefined, I guess. We're going to say, hey, this is empty. Cool. And then we have the main function, mighty crodar. We're setting it to values. And we have glorp, setting it to values. And we have a pointer here. Cool. And we also have glorp here. We're setting it to a bunch of values. And we have crodar, the mighty crodar. We have glorp. We're setting it to a bunch of values. And I was immediately saying, hey, please fix me. Let's see. What's required here is a pointer to the character type. So if glorp needs to be passed, we know the way to pass it is ampersand glorp. Essentially what that's going to do is pass in the reference glorp to the print character function. Notice how this function's C parameter is a pointer to the character struct. Yep, we noticed it all right. Now here's something you haven't seen before. When switching an enum, you don't have to write the full enum name. Zig understands the dot wizard means class dot wizard. When we switch on a class enum value, I see. This is a shorthand syntax. Now, how does it know all this whiz, thief, bard, warrior is pointed to the class type, which class is not the object-oriented class, it's just the name given here. User-defined type to be precise. It works because what we're switching on, that's data type, is the only possible legal values within a switch expression. So it makes sense to write this shorthand. We do this, we've already been doing this similar shorthand when we're printing something and we do this anonymous type thingy. But yeah, here it makes sense. I understand the switch and we're just printing all the list of values. Now checking an optional value and capturing it will be explained later. But we're saying if conditional and we're saying c.mentor. Since this is a pointer, I believe there's a possibility that null can be passed, which is why we're doing an optional check in this syntax. This syntax is extremely similar to how we would handle error unions, where we have if, and if will give it, if will run only if what the conditional evaluates true an actual value, and else will run when an error occurs. I believe something similar is happening here. If, since it's a pointer and we're doing c.mentor, let's see what the mentor is. Yeah, it's a pointer to the struct itself. It's gonna look at this and say, hey, if it's not null, then proceed with this case. I believe that's what's happening, and they'll explain it, and we'll trust it. And we can see this exercise for optionals. We want to trust the process. Again, the goal is to truly understand the low-level implementations and not just rush through and say, I know this language. Because I've done those mistakes before, and even with Go, you never truly appreciate the language if you speed run it. It's better to go slow. Cool. Let's give this a quick run, see if we got the implementation correct. It was pretty straightforward. Yep, it works. We are displaying glorp and each of class wizard, and we see the different values. We have 10, we have 20, and the health is 100. Is that by default? Where's health? Yeah, we've set a default value here. Cool, that makes sense. And yeah, that kind of makes sense. Everything works. We've printed the wizard here, and we're also printing its mentor here. We're saying if the mentor exists, and we can print it. I'm just gonna, just for the fun of it, I'm gonna put null here. How do I know it can be null? The question mark here means it can be null here. So if I pass null here, and we'll comment this out, let's run. Yes, now we see the mentor didn't print. This is really cool. I'm enjoying these exercises, learning more about pointers. Really fun concept, fun, interesting, and moreover powerful concept. Cool, let's do the quiz before we wrap it up. I believe we're at the 35-minute mark. Really good. We kept on track. We did it quick enough, but we also learned the underlying theory to an extent. We still need to do a lot more reading. Cool. We have this beautiful poem here. What's the poem? Elephants walking along the trails are holding hands by holding tails. Okay, that's really funny. It's from Holding Hands by Lenore M. Link. Cool. Let's see the program. We have the standard library, we have the elephant struct, we have letter, trail, visited. So the letter, I believe, is the name of the elephant, ABCD, I guess, and we have the tail. I believe this is, you know what this is? This is literally like a node in a linked list. It's referencing the next possible elephant in the chain. And we have a visited keyword here. Yep, it just signifies whether if we're traversing this linked list, whether we've already seen it or not. Cool, a lot of fun. Let's look at the main function. We're assigning elephant A as a variable where I have elephant C. Now they want us to add elephant B. Let's go add that here. Elephant B is elephant, and the only thing we're going to define at this point in time is B. Now, how does it let us assign only the letter without screaming about the others? That's because we are passing default values here, so we're not explicitly forced to assign it to some value. Cool, that's understandable. Let's keep going. Now link the elephant so that each tail points to the next elephant. Now first let me just print it. The visit elephant function is just running it in a loop and going from the start to the very end, and it keeps track of which all were visited one at a time. This is quite literally linked list, and it's so beautifully expressed through pointers. Cool. Let's just run it first. Yep. So what happened here? Segmentation fault. Beautiful. Why is it saying a segmentation fault? It's saying a segmentation fault because, so let's see this. There's a connection from A to B, and there's a connection from C to A, but there is no connection from B to C. So when this loop runs, it's by default saying if you have not visited it, now this is a circular linked list, right? You can just see it, A to B, B to C, C to A, and then again the loop goes on. To prevent that, we have the visited flag, and flag is nothing but, it was just a terminology that's used by convention, which is used to denote some operation. So as we're going through the loop, we're setting whether we visited or not, and even reading this will clearly say the function visits all the elephants once, starting from the first element and following the tails to the next element. If you did not mark the elephant as visited by setting visited equals true, then this would loop infinitely. Makes sense because this is a circularly linked list. Cool. Now, why did this segmentation fault occurs? I love reading this error. I've heard so much about seg faults and how C, one of the big runtime issues in C is segmentation faults. It's a whole class of errors that I've heard a lot of C devs, inexperienced C devs scream about. Okay, now let's see why this happened. This happened because we're trying to access a memory location from elephant B. So we're saying, hey, elephant B. Whenever this elephant B, we've reached elephant B through the tail, we can print elephant B. We'll say it's visited, but we'll try to access a location in memory held by elephant B. What is that? It's undefined. So there's nothing there. But now we're trying to print something out of nothing. So it fails. Now before I fix this with this simple line of change connecting B to C, I'm going to go here and make this nullable. And let's see what happens. Okay, there's a whole bunch of changes that need to be changed. Let's go. E is equal to E dot tail. And let's make this nullable as well. Cool. Let me clear it. Run it again. Oh, yeah. So it's nullable. How are you trying to do it? We know the if syntax. We just saw it. So I'm going to say something like E dot visited. Now I'm just doing this out of thin air. I haven't done this before, but let's see. Now if E is not nullable, then let's get E again. And now this E inner scoped E takes precedence, but let's say, oh, you're trying to use the same, yeah, capture previous declaration here. Yeah, we're basically saying this local variable shadows the variable outside and saying name it something else. Let's call it Ellie, a cute way of saying elephant. Okay, we can do something like this. I'm gonna see what happens here. Oh, my bad, here. Cannot assign to a constant. Oh, makes sense. Makes sense. Can we say E dot was it E dot tail, right? So what if I do E dot star? This would also fail because we're isn't E dot tail. No, it's next. Next value is E, right? Let's run this. Perfect. This is what I was trying to understand here. So what happened here? We're saying there is elephant A and there's elephant B. A connects to B. B does not connect to anything. It's when we loop through this, now since E points to null, there's nothing to evaluate here, right? E is null, it's over. If it's null, we can't make any checks here. And I believe it's terminating as soon it reaches, it goes from A to B. Um, Even though we're saying elephant dot A is the location held by elephant dot B, I was expecting it to print B as well. I'm just curious. This is me going on a complete tangent. The initial exercise is very straightforward and simple. I already get it. I just want to play around with this for a brief moment. Cool. We have the optional, and we're saying take this variable, assign it to the next one, E. Now E stands for B. When B has come here, it's going to say, hey, have we visited B? No. Why don't we print B? Right? That's what I was expecting. I was expecting B to be printed first. And then it stops. Right? I'm just out of an abundance of curiosity. I'm just gonna fix it with null and then see, and then we'll go back to the original one. Just even if I don't get it, I just want to understand what's happening here to an extent. Only A is printing. Okay. So let's see what I actually did. I took the optional. And we have E. We're printing the first elephant letters. We're setting it to visited, and we're assigning the next value by going to its tail. So E, so tail is null. By default, it's null. Okay, it never got reassigned, is it? Why don't I see anything here when I look at the LSP and VS Code showing it to me? What if I undid all of this? Undo everything except for B, of course, and leave this as undefined. And I go here, what do I see? Okay, it's still the same. It's not showing the next value. Something must have happened here. That's a logical error. A came. We've not visited. A gets printed, which is correct. We'll mark it as visited, and we'll assign it to the next elephant in the chain. And once that happens, the while loop comes here and it'll check, have we visited? B has also not been visited. We know from here. It should immediately print B. Correct? Even though it's by default null, we are assigning it here. Curious. If I do else, NID, and I'm going to say reached else block. Oh, my bad. What happened here? Oh. The anonymous type. It never reached the else block. If E. I don't even know if there's an option with else. Okay, this is curious. It's very, very interesting. Why? Uh, I was trying to understand what happens when we use null and how to handle it. There's optionals here. Um, trying to debug it. We are using visited, which makes sense. Let me think about it a little bit, even though this video might exceed the time limit that I set for it. It's very interesting. The optional syntax is right while it's there. If it's null, you print it, assign it to the tail, e.tail. That's first element A. What if I pass in B here? And what if I pass in C here? Will it also print A or just end at C? Ends at C. Okay. Continuation based on visited being true. So not visited, if you have not visited, right? Will this lead to an infinite loop? Infinite loop of only A. So essentially what's happening is E is of type elephant. It's never going to whatever the next one is. But why would it not? If we look at this piece of code, previously it was e.tail. Yeah, ele.tail. And ele is nothing but the transformation of the optional to a not optional value, if I'm right. And we're saying, hey, just go to the next value. Does it have something to do because it's a constant? It's not a constant, but I mean, it's a loop. It's a de-optionalizing it, I guess, of some sort. Maybe it has nothing in the tail. Yeah, I think there is some trick to this previous example, the way this was doing things. Checking an optional, capturing it will be explained later. This pairs with the, yeah, that we understood it. We know there's a quirk with this optionals. But that's okay. That's okay. We'll circle back to this. I know the next exercise has optionals. We'll hold ourselves, trust the process, and we'll circle back to it. That's okay. But I'm glad we still tried and at least looked into what we'll learn in the future. Let me go back and solve this exercise, which is very straightforward. The exercise itself is very straightforward. It's just the curiosity to keep going and running at pace. Cool. Let's make elephant B element. Yeah, elephant B, and this will solve the seg fault. Elephant C. Cool. We'll say, oh, my bad. It should be a reference, not the struct itself. A, B, C. Now we have the chain of elements created. Yep, fun exercise. We didn't get to the optional portion, but I don't want to jump the gun. We can understand it once we go to the next exercise. But now we've tried something with nulls and we know how to think when we come to the optionals exercise. So still a win, still, even though the output never came. Again, the goal is to understand the language and it's still a win. Yeah, so I think that was a really fun set of exercises to understand pointers. Really great that Ziglings, again, a huge shout out to Chris Bosch and Ziglings for making Zig's so easy to learn and straightforward to these fun practical exercises. It's not just a whole bunch of text. It's like short, sweet, to the point. Huge thank you to Chris Bosch, and as always, a huge thank you to all the um, incredibly talented and incredibly smarted people over at Ziglang building this wonderful language. So yeah, we're well past our time limit. We'll call it there, and I'm excited for our next video on optionals. That's it. See y'all later. Bye.